All right, I'm getting a little faster at this. If you'll notice on your note page, um, there are two sections for the next table, one for weak acid and strong base, and one for weak base and strong acid. We're just going to be completing the weak acid, strong base section in this video. We'll do the last column in the next one. And this is just kind of an overview. There's also another format for this on the last page of your note packet. And I'm going to give you one other one just so that you've got some different ways to take a look at it. Um, Part of the reason that students don't tend to be super big fans of titrations is that in all the other examples of titrations besides strong acid, strong base, we really have to pay attention to what we have present. Sometimes we can just have weak acid. Sometimes we can just have weak base. Sometimes we will have strong acid. Sometimes we'll have strong base. And sometimes we'll have both after we account for any additional or any additions of strong acid or strong base. And depending on what we have present, influences how we calculate the pH of that mixture or determine what's present. So again, we're going to focus just on weak acid and strong base in this particular video. So initially, before you titrate, and you would always titrate with your strong component, the only thing that you have present in your flask would be the weak acid. And anytime we want to find a pH of just a weak acid or a weak base, we do that with equilibrium. We have to find its concentration and use its Ka or Kb value to determine its pH. With weak acids and strong bases, however, once you start adding the strong base to it, you generate a buffer. You don't just have weak acid, you now have its conjugate base. If we go back to those equations we talked about with buffers, remember every time we added strong base to a weak acid, we formed its conjugate base. We need to figure out how much of that weak acid and conjugate base we have present. And once we've figured that information out, we can find pH again using our Ka, keeping in mind we'll have components for a reactant and the product, or we can find it using Henderson-Hasselbalch. At the equivalence point, you have used all of your weak acid, you have used all of your strong base. The only components that you have present would be water and the conjugate of that weak acid, your conjugate base. And bases are going to have more of a role in determining the pH than water. So we would have to use our equilibrium expression for that conjugate base, along with its Kb value to determine its pH. You'll notice, I didn't mention this initially, your pH is going to be acidic. It's not going to be as acidic as the strong acid, but it will be acidic. By the time you get to the equivalence point, which will be more gradual than we saw with the strong acid, strong base titration, your pH will now be in the basic range. If you keep adding strong base to your mixture, and you guys saw that when you were trying to turn your solution a light pink, it would get even brighter and brighter with the addition of phenolphthalein because you would make your solution even more basic. There would be nothing to neutralize the excess strong base that was being added. You would still have the weak base that formed, but strong base is going to have more of an influence on pH than weak base. And so you would need to figure out your concentration of the strong base that is remaining after you've neutralized some of it and use your pOH equation. I'm sorry I didn't leave you enough room to write pOH equation. And that along with the final volume to determine the pH that's present in your mixture. So we're going to walk through each part of that. You've got a whole page to do the next example problem on because I wanted you to have plenty of room to walk through the steps with this problem. So an example of a graphical representation of this, again, you'll notice that your pH is starting much higher. You're dealing with a weak acid. You'll see that it is gradually shifting up a little bit more than what we saw previously. But that when it reaches the equivalence point, it will be basic when you no longer have your buffer present. And then after that, you just have excess strong base that is determining your pH, and your pH is definitely very basic. So once you get past the initial, once you start adding base after that initial point, time zero, all the way up to the equivalence point, this whole region is considered to be a buffer region where you have both the weak acid and you have the conjugate base. Any point in that buffer region, when you have both weak components present, you can use Henderson-Hasselbalch to determine your pH. And there is a special point that's kind of noted in part B if you look at the graph, and that would be when you are at the halfway point. When you have added the volume of base has made it so that you have equal amounts of the weak acid and the conjugate base. At that point, the two having the same concentration would cancel each other out, and your pH would be equal to your pKa. Um, that's what we did when we were determining the Ka of our weak acids. We wanted to have equal amounts of the two components so that only the hydrogen influenced the pH, and the hydrogen concentration was determined using your Ka. Okay, so in this first component, we're going to be dealing with the same reaction all the way through. We have hypochlorous acid, a weak acid. It has a Ka of 3.5 times 10 to the negative eighth. It's going to be titrated with a strong base, lithium hydroxide. Again, OHs are always going to be your strong bases. I want to find the pH of the solution after I've added different amounts of LiOH. In this first particular example, we haven't added any LiOH yet. So the only component that's present in our mixture is the hypochlorous acid, a weak acid, and the only way we know to find the pH of a weak acid is using its Ka. Again, weak acids are going to donate protons just like strong acids, but they're going to produce their conjugate base, and they are going to produce hydrogen ions. And that definitely should be a double arrow. Sorry, I went through this twice. I missed some stuff because it is an equilibrium reaction as opposed to a stoichiometric with strong. So with our Ka expression and knowing the value for Ka, we can set up our expression. We don't know the conjugate base, we don't know the hydrogen concentration, but we know that they should be the same. We do know the original amount of the hypochlorous acids, zero point 0.1. If we compare zero point 0.1 to 10 to the negative eighth, those are far enough apart that you should be able to omit the change in X that would occur with the weak acid. I think I did this through with both of them and I got the exact same answer. When I calculated X, I got it to be 5.9 times 10 to the negative fifth. Again, that is your hydrogen concentration, which you can use to find your pH. And I'm getting that hydrogen concentration again because it's from the Ka expression. If it was a Kb expression, you would be getting hydroxide. pH being the negative log of your hydrogen concentration will be the negative log of that value, and it would be 4.23, 2 decimal places for the 2 sig figs and the concentration. So all we had was a weak acid, so we find the pH of a weak acid just like we've done throughout the previous unit before we had this little break. In our next example, we are adding hydroxide. We are adding 25 mils of it. So when we are adding strong base, we have to stoichiometrically determine how much of the acid got consumed, whether the acid or the hydroxide was our limiting reactant. We don't have any of the hypochlorite ion present initially, and we don't have any water initially. This should be a single arrow because we are completely consuming one of those two components. Anytime you have strong, you're going to be consuming. To determine how much we're consuming, we need to use our moles. So if we look at 100 mils of 0.1 molar hypochlorous acid, that means that we're going to have 0.0100 moles of HClO. And if we look at the lithium hydroxide, there's 1 OH present. We would take 25 mils, convert it to liters, 0.0250, and then multiply it by the 0.100 molar LiOH to get 0.00250 moles of hydroxide ions. And again, we don't have any of the hypochlorite present initially. Looking at the two reactants, we can see that the hydroxide is a smaller quantity present. Everything is in a 1-to-1 ratio, so the hydroxide is going to be completely consumed. Some of the hypochlorous acid will be consumed, but we will be making some hypochlorite ions, the conjugate base of HClO. So once we have accounted for the hydroxide being consumed, we now have weak acid and we have conjugate base. That would be a buffer. Again, anything up to the equivalence point, but once we start adding base to this, is going to consist of some form of the buffer. And so we can use Henderson-Hasselbalch or your Ka expression to determine this. If you use Henderson-Hasselbalch, you don't have to change these back into concentrations. If you use Ka, you do have to change it back into concentration. Pretty sure pH equals, let me go through this and take a look. So pKa is going to be the negative log of our Ka, the 7.46. And if we just substituted those in I'm doing something in my head, y'all. I'm sorry. If you use your Ka expression, you would get your hydrogen concentration, but your hydrogen concentration, would it be in moles or molarity? I believe it would be in moles, so you would still have to divide it by the new volume to get your pH. I would encourage you to stick to using Henderson-Hasselbalch so that you don't have to worry about switching back to concentrations, but it is your call. If you're using your Ka expression, you need to go back to concentration. If you're using Henderson-Hasselbalch, you can leave it in moles because it is a ratio. And when you do the math through, we get that the pH has increased. It's gone up to 6.98, and that might seem like a big jump, but remember, we didn't have any base present initially, and now we do. We're going to see that it's going to continue to increase as we add strong base, but we're not going to see it stay pretty close to where it was at the beginning, like we saw with the strong acid, strong base. But we will see in the buffer region that the pH is only going to change slightly. As we move on, we'll do the same thing with part C. We've got our 0.01 moles of the hypochlorous acid. This time we have 50 mils of the lithium hydroxide being added. So we have 0.00500 moles of OH minus, and we have none of the hypochlorite ion to begin with. Our limiting reactant, again, is the hydroxide. So when we take the hydroxide and consume it completely, we're going to generate 0.00500 moles of hypochlorous acid and 0.00500 moles of hypochlorite ions. We have equal amounts of the weak acid and the conjugate base. The pKa is going to be done just like we did Ka before by taking the negative log of that Ka value. And you'll notice that the base and the conjugate acid having the same mole amounts will give you a log value equal to 0 because they aren't going to influence the pH since there are equal amounts present. Your pH at this halfway point, which is 50 mils, would be your pKa. So what this does tell us, besides being the halfway point, is that when we get to 100, our next example, we will be at the equivalence point because 50 is getting us halfway there. At this point, we're going to start to see that ratio increase where we're going to have more base in the numerator and less acid in the denominator. We're going to keep consuming the acid until we have destroyed our buffer, until we no longer have any acid present. So in part D, the initial amount of HClO does not change, but we now have the same amount of hydroxide, 0.1000 liters times 0.1 molar, gives me that 0.0100 moles. I have no hypochlorite ions to begin with. Since both the reactants have the same amount, they're both limiting, and they're both going to result in the same amount of hypochlorite ion being generated. So when we get done with the stoichiometric part of this problem, the only component we have that can influence the pH is the ClO minus. That would be a weak base. Well, to find the pH of a weak base, we have to go back to our Kb expression. We can't use Henderson-Hasselbalch anymore because we don't have any acid present. Henderson-Hasselbalch can only be used when you have the buffer, the weak acid and the conjugate base. To go back to our Kb expression, we need to find the concentration of ClO minus, because when we're dealing with Ks, we have to be in concentrations. So we take the 0.0100 moles of hypochlorite ions and divide it by its new volume, the 100 mils of acid and the 100 mils of base, 0.200 liters, to get its concentration to be 0.0500 molar. When ClO minus is added to water, it produces the hypochlorite ion. So you might think, well, didn't we just get rid of it? We did. But it's able to generate hydroxide, and that hydroxide is what's going to determine our pH. Again, that should be a double arrow too. Sorry. I did some edits on this one, and apparently I did not pay enough attention to my arrows. My Kb expression would need to be used because I'm producing hydroxide. You can get the Kb value off of your chart, or you can use the Kw and is equal to Ka times Kb to solve for Kb, which in this case was 2.9 times 10 to the negative 7th. And again, that is the ClO minus Kb, and it is on your chart. Or also Ka times Kb is equal to 10 to the negative 14th. Now that I know Kb and I know the concentration of ClO minus, I can solve for the hydroxide concentration. Again, the concentration of ClO minus and the Kb are far enough apart from one another in powers of 10 that you should be able to disregard the change in concentration of ClO minus. And when you solve for X, you get that hydroxide is 1.2 times 10 to the negative 4th molar. The pOH would be the negative log of that value, 3.92, and 14 minus that would give me my pH. Again, at this point, I'm at the equivalence point. I only have base present. I would expect the pH to be basic, and indeed it is. In the last example we're going to do with this problem, we are going to have an excess of hydroxide added because we have the same amount of HClO that we started with, but now we have 125 mils. We're past that 100 mil mark. When I take that volume and molarity, I get that I have 0.0125 moles of hydroxide ions. So my limiting reactant is no longer the OH minus, now it's the HClO. So 0.01 is subtracted from both reactants and added to the ClO minus. The HClO goes to 0, no more buffer. And now I have two bases present, 0.0025 moles of hydroxide and 0.0100 moles of ClO minus. Even though I have 4 times the amount of ClO minus, the hydroxide being a strong base is going to win out every time. And I would use my pH calculations for a strong base to determine the pH of this mixture. To do that, I need to know the concentration of hydroxide. So I take the moles that I have of the hydroxide that are remaining, and I divide it by my new volume, the 100 and the 125 mils added together, which gives me a concentration of 0.011. When I find the pOH of that concentration, I get that it's 1.96. Again, very basic because strong base is determining the pH at this point. And when I find the pH of that 14 minus the 1.96, I get that it's 12.04. So this is the end of the second video with titrations.